Hey y'all, how you doing? Hope you're having a great day. Today I'm going to be continuing the series on vibrational spectroscopy, and we'll discuss Rayleigh and Raman spectroscopy, or you could call them Rayleigh and Raman scattering. So, the thing to know for this video is molecules have electrons that orbit them, and you can never find the electron at a precise location. There's only a probability of finding it at a precise location. So a chemist would say molecules are surrounded by electron clouds, and it's like a cloud of probability. So you can view a molecule as a couple nuclei, which I'll draw as plus signs, surrounded by an electric cloud. So these plus signs are two nuclei, or the center of two different atoms, surrounded by a probability of finding their electrons. And for now I'm just going to draw that like this. So these plus charges are nuclei, and this shaded area is the electron cloud. So this electron cloud can distort around the nuclei, or sort of vibrate back and forth between it, like a harmonic oscillator. And the ease to which the electron cloud is pulled from the nuclei is called polarizability. And if you put this molecule in an electric field, the electron cloud will distort to its lowest energy state to accommodate that electric field. So, in a similar way to how I drew a dipole with an electric field, I'll draw how the electron cloud moves relative to the nuclei in an electric field. So for no electric field, we would have the picture above. And let's have an electric field pointing up, which you can make an electric field by putting a bunch of positive charge here, a bunch of negative charge here. So if you put this inside here, well, the electron cloud is going to want to go towards the plus charges, and the nuclei are going to want to go towards the minus charges. Electric field up. So we can draw the positive charges down here. They remain the same distance away as in the no electric field case. But most of the electron, there's a higher probability of finding the electron towards this positive area of the electric field. So essentially the electron cloud's going to distort in the direction of electric field. So the electron cloud distorts in direction of E field. Now let's point the E field down. Well, what's going to happen? Okay, it's like you got a bunch of minus charges up here, a bunch of plus charges down here. Well, it's just going to be the opposite of this. So you're going to have the electron cloud's going to be attracted to the positive. Well, it's the same thing. It's going to be attracted in the direction of the electric field. But now the direction is down instead of up. So it's more likely to find the electron cloud pointing down rather than up in this case. So, imagine you have an electric field going up and down really fast past this molecule. Or, in other words, you have electromagnetic radiation going past this molecule. Well, what's going to happen? This electron cloud, imagine the nuclei are stationary, the electron cloud is going to slosh back and forth between the nuclei. And the sloshing will cause electromagnetic radiation to scatter or sort of bounce off the molecule. So the sloshing will cause electromagnetic radiation to scatter. So it's like you have a light wave coming in here. It's going to scatter off that and bounce off in some other direction. Now, let's look at this from an energy standpoint. So we'll draw the potential well, which is shaped like a Morse curve. Or if you want to think in simpler terms, just think of the harmonic oscillator. And here's energy. So let's say this is our ground electronic state, and we have vibrational states within this. And I talked about this in my last video. And as you go up, the levels get closer and closer together, and they approach an asymptote. And this is V equals 0, V equals 1, V equals 2, for the 0th vibrational state, first, second, third, so on and so forth. So this axis is energy. This axis is bond length. Just considering one bond here. And this is the equilibrium bond distance R0. So whereas in infrared spectroscopy, we could only go up one level, and the radiation was actually absorbed, when radiation gets scattered, it gets scattered either elastically or inelastically. So inelastic scattering would look like this. Oh, well, inelastic means there's no loss of energy. No loss of energy. So what would happen is you have radiation coming in. It could be of any energy, but say it has an energy equal to this. It comes in and interacts with a so-called virtual state, and then the molecule returns back to the same exact vibrational state. So these two arrows would be inelastic scattering. Elastic scattering, on the other hand, there's an exchange of energy in elastic scattering. So you can have that two ways. If you start in V equals 0, well, you could go up in this case, or you could come back down and end up in V1. So notice, if this first arrow here is incoming radiation, and this dotted arrow here is your outgoing radiation, well, your outgoing radiation lost energy. So a loss of energy with respect to loss of energy in the incident beam. We would call that Stokes scattering. Well, so I forgot to mention, inelastic scattering is also Rayleigh scattering. So there's no loss of energy in inelastic or Rayleigh scattering. It's kind of the same thing, whether you want to say inelastic or Rayleigh. Elastic scattering, and there's two types, there's loss of energy or gain, but both types are Raman scattering. And when you lose energy in your incident beam, it's Stokes, just like these two. When you gain energy in your incoming beam, it's called anti-Stokes. And that would look like this. Well, you would have to start in a vibrationally excited state, and you have incoming radiation. It could come up to here, doesn't necessarily have to go to this same virtual state, and it could come all the way back down to V equals 0. So essentially, your beam gained this much energy, which we learned in the last video is just h nu, where nu is the frequency between these two states. We'll call it nu naught. And the same thing with the Stokes, except you lost an energy h nu. Okay, so that's the basis of scattering type spectroscopy, which is also, so mainly when people do Rayleigh or Raman spectroscopy, it's mostly Raman. You get more information. It's with respect to the vibrational states. Now you can also do it with rotational states, but instead of drawing these arrows here, so I'm not drawing it, but there's rotational states inside each one of these vibrational states. And the same thing would happen, but you would have to scale down all the arrows. And the same terms would apply, but instead of, I should really call this diagram vibrational inelastic or elastic scattering, but I'm being more general here. And if you do it with respect to the rotational levels, it'd be just rotational inelastic or elastic scattering. So the vibrational Raman spectroscopy, which is by far the most practiced, and there's also rotational Raman spectroscopy. And similarly to IR, there's selection rules. So the selection rule for Raman spectroscopy is that the change in the polarizability with respect to the normal coordinate cannot be 0 for a transition to occur. And I'll sort of explain why. So the Raman scattering intensity is proportional to this induced dipole moment squared, or the square modulus of the induced dipole moment. And the induced dipole moment is equal to your polarizability times your E field. But most E fields take the form of some amplitude times a cosine wave. We'll call it cosine omega t. And we'll call the omega omega E for omega of the electric field. Okay, but you can expand the alpha in a Taylor series like so. Alpha would equal alpha naught plus d alpha dq, where q is the ith, well, q sub I, where q sub I is the ith normal coordinate, times the normal coordinate. But you can just write the ith normal coordinate as, so qi equals some amplitude times a cosine. So this is the value of the ith normal coordinate. It's just going to vibrate. That there's going to be an ith vibration, and we'll call it omega I. So the ith vibration changes with the frequency omega I. And so if we plug this back in here, we get this. Alpha naught plus d alpha dqi times a cosine omega it times e naught cosine omega e t. And we can distribute this. So we get mu induced is equal to alpha naught e naught cosine omega e t plus d alpha dqi a cosine omega it times E naught cosine omega e t. And then using the following trig identity, we can expand the second term as a sum of two terms. So we're using the trig identity that says cosine A times cosine B is equal to half cosine A minus B plus cosine A plus B. We're using that trig formula to get the following. Okay, and finally we end up with three different terms. And these three different terms correspond to the three different types of Rayleigh/Raman scattering that I spoke of before. So this first term corresponds to the Rayleigh scattering, because you can see it doesn't matter the frequency of the vibration, of the ith vibration, it only matters what frequency it comes in. So if light at 500 nanometers comes in and Rayleigh scatters off the molecule, then you're getting light with 500 nanometers coming out. And now this, you can see there's a decrease in energy because, well, the frequency is going to decrease. Well, depending on if the electric field is larger than the omega ith vibration. So this would correspond to Stokes scattering. And this one would correspond to anti-Stokes because the frequency is going to increase. So the intensity is going to be proportional to the square of this, and I'm not going to square it out. Okay, so that's a little background on Raman spectroscopy. I hope you enjoyed that, and have a great day.